Hi everyone. Let's talk about databases now. So in your system design interview, how good your design is and how well it can scale depends very much on the choice of database that you have used. Now, databases generally do not impact your functional requirements. So whatever your functional requirement is, you can satisfy that by using any database that you want. But normally, the non-functional requirements are the ones which are impacted by the choice of database. So let's just say you have certain query patterns or certain kind of a data structure or certain kind of a scale to handle. There are different set of databases optimized for different kinds of such things, right? So based on the choice of database, it would impact how well your design can scale up to the requirements that are given as part of your non-functional requirements. So in this video, what we'll do is we'll go over some very common use cases that normally you might come across in your system design interview, and then look at some of the potential solutions or possible set of databases that you can use to handle those scenarios. Now, normally the choice of database depends on a couple of factors. The very first thing is the structure of the data that you have, whether it's a very structured data or a totally non-structured data, that is one of the factors. The other factor that impacts the choice of database is the query pattern that you have. And the next obvious one is the amount of scale that you need to handle. So all these three factors would make a difference into the choice of database that you want. Now in this video, we'll look at some common obvious ones in the beginning, and then towards the end, we'll look at the SQL NoSQL comparison and a combination of certain kinds of databases that can help you solve a real world problem. Let's talk about caching solutions. So whichever system you are designing in an interview, you would definitely have to use some caching solution there. Now there are a lot of use cases for caching. Let's say if you are querying a database and you do not want to query the database a lot of times, you could cache the value in a cache, right? Alternatively, if you are making a remote call to a different service and that is having a high enough latency, you might want to cache the response of that system locally at your end in a caching solution, right? And there could be a lot of use cases for caching. Now, generally, the way caching works is you have a key and you have a value. Okay, so key normally is whatever your where clause is in a query or whatever your query params or the request params are when you're making an API call. And value is basically the response that you're expecting from the other system, right? So all of these kind of values would be stored in normally key value stores. Now, very common use solutions are Redis. You could also use Memcache. You could use etcd. Hazelcast is picking up a lot these days, so you could use any of them. Normally, in the videos that I make, I tend to use Redis because that is a very battle-tested solution and it is used by all the big companies in the world and it's fairly stable. So, in whatever system design you have where you have to use a caching solution, you could use a Redis. Okay, I'll just note it down so that you can refer it. Redis is the solution for caching. Now, again, this does not mean that you cannot use anything else. You could use any similar solution and that would work just fine. Next, let's look at some file storage options. So let's just say you are designing a system like Amazon, where you are having various products that you are selling. Now the sellers would be uploading product images, maybe product videos, right? You need a data store to store those images and videos. Similarly, you could be potentially building a system like Netflix, which has videos altogether, and you need a storage to support videos. So wherever you have a image, video kind of a thing, there we'll use something called as a blob storage. Now, these are not really databases. Databases are fundamentally meant for things where you can query on. Now, a file is not something which you will normally query on. You will just serve it as it is, right? So then is when blob storage is coming. Now there are a lot of providers for that. One of the most common ones and a fairly cheaper one is Amazon S3, and it is a fairly good system used by a lot of companies. So whenever you have a requirement of storing images, videos, and anything of that sort, you could use Amazon S3 as a data store. Now, along with S3, you might want to use something called as a content delivery network, which is often called as a CDN. Now, CDN is generally used for distributing that same image geographically in a lot of locations. So let's just take a simple example that you have a product image that is stored in Amazon S3 as a primary data source. And there are a lot of people coming from throughout the globe who are accessing that product. So you might want to distribute that image into various servers across the globe so that individual people can query them in a much faster way as compared to querying an S3 which is probably located in a couple of locations, right? So for all blob kind of content, you would then be using something like a For all blob, you would be using something like a S3 plus a content delivery network, and that should be fairly fine on all your interview questions. Now, the next very common use case that you might encounter is, for example, if you're building a product like Amazon and you need to provide text searching capabilities on various products. So, a seller has uploaded a product with a particular title, some description, and you want users to search that, right? Now, that searching would be provided on a text of title and on the text of description. Very similar use cases would be when you have a product like Netflix to build and you want to search, give the option for the users to search on movie names, movie titles, genres, maybe cast and crew names, and all of that. Or alternatively, you might be designing something like an Uber or Google Maps kind of a thing where you want to provide text searching capability with support for fuzzy search. So for all of these kind of use cases, you would be using something called as a text search engine. Now, a very common implementation of a text search engine is provided by Elasticsearch and Solr, and both of them are built on top of something called as an Apache Lucene. Now, Lucene fundamentally provides these text searching capabilities, and that is then being used by both of these products, Elasticsearch and Solr. Okay, so the next use case, I'll quickly write it down, is your text search, which is Elasticsearch and Solr. Now, one more thing that they support is something called as a fuzzy search. So what is that? Is I'll quickly go over that. Let's say if you're searching for the word airport, okay, and let's say if the user typed in airport with a wrong spelling, okay, this O and R are interchanged, right? Now, if a user searches for this and you do not return back any result, that's a bad user experience, right? So you need your database to be able to figure out that the user did not really meant this thing. The user actually meant airport, right? Now, how does that database identify? So this word can be converted into the correct spelling of airport by changing two characters, right? R needs to be converted into O and O needs to be converted into R, right? So this is at an edit distance of 2, right? So you can provide a level of fuzziness that your search engine needs to support. This has a fuzziness factor of 2, which is the edit distance. Normally there are a lot of other factors also that come in, but this is roughly how fuzzy searching is implemented in most of the solutions. So wherever you have any search capabilities, there you use either Elasticsearch or Solr. Now, one very important thing about both of these are not databases. These are search engines. So the difference between a search engine and a database is whenever you write something in a database gives you a guarantee that that data wouldn't be lost. Okay. Now, both of these data stores don't give you any such guarantee. They claim that they are giving a good enough availability and redundancy and all of that, but potentially data could be lost. So you should not keep any of these as your primary source of truth. Your primary data source should be somewhere else, and you could load that data into either of these systems to provide the searching capabilities, and these two are very efficient at search. Next, let's look at what do you do if you want to store some metrics kind of a data. So let's say if you are building a system like Graphite, Grafana, or Prometheus, which is basically an application metrics tracking system. So let's say if the use case that you are given is a lot of applications are pushing metrics related to their throughputs, their CPU utilizations, their latencies, and all of that, and you want to build a system to support that. Then is when comes something called as a time series database. Now think of time series database as an extension of relational databases, but with not all the functionalities and certain additional functionalities. So regular relational databases that you have would have the ability to update a lot of records, right? Or they would also give you the ability to query random records. But whenever you are building a metrics monitoring kind of a system, you would never do random updates. You would always do sequential updates in an append only mode. So if you are put an entry at time t1, the next entry would be at time t2, which is greater than t1. The next entry would be at time t3, which is greater than t1 and t2, right? So it's a append and only write mode. Also, the read queries that you do, they are kind of bulk read queries with a time range, right? You query for last few minutes of data or few hours of data or few days of data, right? But you don't do a random read or a random update. Now, time series databases are optimized for this kind of a query pattern and input pattern, right? So there are a lot of time series databases. InfluxDB is one of them. OpenTSDB is one of them. So you could use either of them if you have that kind of a use case. I'll quickly write this thing also. For time series, you will use something called as a Open TSDB. It stands for Open Time Series Database. Okay. The next use case is when you have a lot of information and you want to store all of that information of a company in a certain kind of a data store for various kind of analytics requirements. So let's just take an example of something like an Amazon or Uber or any system design where you want to provide analytics on all the transactions. You might want to provide analytics like how many orders I'm having, what geographies are giving me, what revenues, which is the most sought after item, stuff like that. Okay. So where you want to do analytics on the data of the whole company, there you need something like a data warehouse. Okay. That basically is a large database in which you can dump all of that data and provide various querying capabilities on top of that data to serve a lot of reports. Now, these are generally not used for transactional system. These are generally used for offline reporting. So if you have that kind of a use case, then you can use something like a Hadoop, which can very well fit in the for that purpose, where you put in a lot of data from various transactional systems and then build a lot of systems that can provide reporting on top of that data. Now, let's look at slightly tricky scenarios where you might want to choose between a relational and a non-relational database. So the very first thing that helps you decide what kind of a database do you want to use is the structure of the data. So if you have a very structured information, then possibly a relational database makes sense. Now, what is a structured information? It would be an information that you can easily model in form of tables, and tables would have rows and columns of information. So, for example, if you want to store a user information, something like a user profile on any social network, it would have name, email address, city, phone number, bunch of very standard information that each user will have. That would be a structured information. Okay. So if we try to make a flowchart of how to decide which database to use, this is how it would look like. Okay. The very first choice that we need to make is whether we have a structured data or a non-structured data. Now, let's say if we have a structured data, the next question that we need to ask ourselves is, do we need any atomicity or transactional guarantees from the database or not? So let's just say that you are building a payment system which supports a feature like somebody can transact money from their account to somebody else's account, right? Now, fundamentally, at the very core of it, it will have two queries. One of them will reduce the amount from the person's account, and the other query would add the amount into the beneficiary's account, right? Basically, reducing from account A and adding into account B. Now your database should be able to provide you certain guarantees which wrap both these query into transactional boundaries saying either both of them would execute or both of them would not execute. But it should never happen that amount has been debited from account A but not credited into account B, or credited into account A but not debited from account B. Something of that sort should not happen. Also, it should provide you some consistency saying if you have done a transaction, the next call that you make to fetch the account balances, it should reflect the amount. It should not be that sometimes it is reflecting the correct amount, sometimes it is not reflecting a correct amount, right? So if you have that kind of a requirement wherein you are building a payment system or an inventory management system where you have the count of number of products that you have while people are buying them and the count needs to reduce, for all of those kind of scenarios, you that would fall into that yes, you need an atomicity, you need consistency, you need transactions, then basically you need to use a relational database. Okay. Now there are multiple providers of relational database. You could use any of them. Some of the very common ones are MySQL, Oracle, SQL Server, Postgres, and there are a lot of them. I've just mentioned the common ones. It does not mean that you cannot use any other database of your choice. You feel free to use any database which provides you asset guarantees. Okay. Now let's say you have relational data, but you do not need asset guarantee. Let's say you are just storing user information which does not have any use case of these atomicity requirements. You could still choose to use a relational database or you could choose to use a non-relational database. It wouldn't make too much of a difference because normally you would be easily be able to map a structured data into a NoSQL model. So either of these scenarios would be fine there. Now, let's say you do not have structured data. So what do you do? So there are a bunch of scenarios in which your use case might fit in. So maybe you are trying to build a catalog kind of a system for an e-commerce platform like Amazon, which has information of all the items that are available on that platform, right? So let's just say if you are building that catalog for Amazon, and if we take certain examples, so let's say there is an item like shirt. Now each item would have certain attributes. A shirt would have an attribute like a size could be large, a color could be red, something of that sort, right? If you have a refrigerator, it would have a volume like 200 liters, 400 liters, or whatever. It would also have a power saving mode like 3 star, 5 star, whatnot. So those are the attributes of a refrigerator, right? Similarly, something like milk would have quantity and an expiry date, right? Now, normally when you are on an e-commerce platform, you not only need to see these attributes, if it is just about seeing them, you could kind of dump it as a JSON and store it in any database of your choice. But normally you would also want to query that. Now, querying on a JSON or random attributes is a bit tricky on relational databases, but there are certain kinds of databases that are optimized for those kind of queries. Okay, so these are the databases where you have a lot of data, not just data in terms of volume, but in terms of structure. So if you have a lot of attributes that can come in and a wide varieties of queries that can come in, then you fall into this category. And if that is the case, then you need to use something called as a document DB. Now there are a lot of providers of document DB, MongoDB, Couchbase are some of them. Earlier we looked at Elasticsearch and Solr for text searching. Those are also special cases of document database. Now let's just say your data is not relational and you do not have complex queries. You have a couple of straightforward queries. You could still use a document DB if it doesn't fall into the third category. Now, what's the third category? Let's say if you have an ever increasing data. What do I mean by ever increasing data? So let's take an example of Uber. So all the drivers of Uber are continuously sending location pings. So let's say there are some number of drivers and they kind of translate into X number of location records per day, right? So there would be X number of records inputted per day, right? But this X would not be a constant. It would be a growing number. Why? Because the number of drivers of Uber are increasing day by day, right? So this data would become probably X on day one, oh, additively 1.1x on day two, 1.2x on day three, so on and so forth. So it would not be increasing in a linear fashion. It would be increasing, but in a more than a linear fashion, right? So that is what I'm calling a ever increasing data. Plus, if you have finite number of queries, so let's say if you want to track location pings of drivers, the most important query that you will do is find all the location pings of a driver with whose driver ID is something, right? So if you have less number of queries but a large amount of data, then these kind of databases would be the best choice for you. This is something called as a columnar database or column-oriented database, and Cassandra and HBase are the most used and most stable options out there for these kind of scenarios. Now there would be a lot of other alternates as well, but these are the most stable ones and have been battle tested again for a lot of years. So I would recommend to use either of these two in such kind of scenarios. Now in my videos, I generally prefer using Cassandra over HBase. The only reason being Cassandra is not very heavy to deploy. HBase generally tends to have a lot of components that it comes with, but performance-wise, both of them are roughly similar. Each of them have their pros and cons, but in a design interview, it wouldn't matter which one do you use. Now, what if you don't have any of these? What if you don't need ACID, you don't need these wide variety of data types and query types, and you don't have an ever increasing data? Then you can use any database of your choice. Then it would basically be a low scale system having a very small number of queries on a very small number of attributes on a very small size of a data set. You would generally not get these kind of requirements in a system design interview, but if you get, you could use any of these unless it's something that we've already talked about, which are one of the special cases in some other scenarios, right? So if it's not that, you could use any of these databases and that should be fine. But normally, when you are in a system design, you would not get a design that you will be satisfied by just one of these databases. So let's look at slightly more trickier real world scenarios. Now, let's take an example of us building an e-commerce platform, something like an Amazon. Now, when you are managing inventory on that side, you want to make sure that you are not overselling items. So let's say there is just one quantity of a particular item left, and there are 10 users who want to buy that. You want to have this asset properties there to make sure that only one of the users should be able to commit the transaction. Other users should not be able to commit the transaction, right? You can put constraints and all of that on there. Now, it would make sense to use a RDBMS database for the inventory management system of a system like Amazon, or maybe an order management system, right? But if you look at the data of Amazon, it is an ever increasing data, right? Because the number of orders are additive. Each day, new orders are coming in. They cannot purge the data due to a lot of legal reasons. Plus, the number of orders are also increasing. So it naturally fits into this model, right? Where I'm recommending to use a Cassandra. So what you could use is a combination of both of these databases. You could use MySQL or any other RDBMS alternate for storing data about the orders which are just placed and not yet delivered to the customer. Once the item is delivered to the customer, you can then remove from this RDBMS and put it into a Cassandra for as a permanent store. Right? I have walked through this implementation in much more detail in the Amazon system design. So I would recommend to have a look on how a combination of database can become a very powerful choice there. Now let's look at another example. Again, taking an example of Amazon. Let's say if you want to build a reporting kind of a thing, which lets you query something like get me all the users who have bought sugar in last 5 days, right? Now, sugar is not a product. There are a lot of sellers selling different sugar alternates of different companies, maybe of different qualities, maybe, right? So, sugar would then be like a lot of item IDs, right? And on top of those, a lot of item IDs, there would be a lot of orders, right? Now, again, I'm saying that orders would either be in Cassandra or in this, right? But if you are doing random queries where some you might want to query on who bought sugar, who bought TV, who bought TV of certain quality, who bought a fridge of certain quality, that kind of logically goes into a model where I was recommending to use a document DB, right? Now, what you could do is you could store the querying part over here, right? You could basically say that I'll store a subset of order information into a MongoDB which says that user ID so and so may had an order ID so and so on some particular date which has these 10 item IDs with certain quantities, right? On this database, you could run a query which will return you a list of users and list of orders, right? And then you could take those order IDs and query on both of these systems, right? So here we are using all the three systems in combination to provide various querying capabilities, like which user bought what kind of use case, right? So in any real world scenario, you would have to use a combination of such databases to fulfill the functional and non-functional requirements that you have. Now, all of these being said, this is just an indicative cheat sheet of what database fits well in what kind of a scenario. Okay, when you are in an interview, you could use this to kind of get done with it. But if you're actually using it in a real world system, I would recommend to read a bit more about it to choose which out of these few do you want to actually use, right? Also, there are a lot of other databases that I have not talked about, which are basically examples of RDBMSs or example of columnar databases. It does not mean that these are the only options. There are a lot of other options out there. You could explore them and use those as well. So yeah, I think this should be a good enough list for a database choice given a certain use case. Thanks for watching.